automatic shorts. Can't give up.
Oh my goodness. All right, everybody, let's get started. A couple things. So I know it's an exciting week because I know it's, for those of you in 321, you've got the big lab, the concrete lab, isn't that today? Tomorrow. Oh, okay. Air, slump, cylinders, whole 9 yards. So, literally, yards of concrete. That's a joke, a very funny one. Just a quick housekeeping item on where we're at. I know I'm a little behind on getting everything uploaded with attendance, and I think I still need to upload the lecture recording from the last time, so I'll try and get that done relatively quickly. I know homework 5.4 is graded and 5.5 is being graded. How did the homework with internal hinges go? Was that straightforward? Okay, good. Now I want to be clear on something. I'm assigning a homework today, but it is not due on Friday. It's due on Monday, okay? It's due on Monday primarily because your first submittal of your project is due on Friday. So I do my best to try and ensure you don't have two things due at the same time. I don't like that. So that's why I pushed this assignment down a bit. And so on Friday, we'll begin the discussion of beam deflection. And so I won't have an assignment for you on Friday on that anyway. So it's kind of a perfect gap. It's a perfect lecture for that gap. Really, I'm curious before we begin. So this problem that we're going to do today is not going to take the full 50 minutes. And so I wanted to first off open and see if anybody had any questions about the first project submission. How many of you have already started working on it? Okay, good. It's not, it shouldn't be a lot of work. And I know that a couple of you have already submitted it. Again, all I need are 3 truss elevations. I need you to verify that they meet the geometric constraints so that they all meet the truss length, they fit within the envelope, that no member exceeds the maximum length limitations, that they all have an IT of 0. That's it. No actual method of joints or method of section analysis on that. And I mentioned this before, but the reason I don't want you to analyze the truss on this submission is because we're going to do that later with software, okay? And you'll see what I mean when we get into that aspect of it. You also need to choose one for final design, and you need to describe the reasoning that you've chosen it. So it could be you just like the way it looks, you think it matches the aesthetics of the campus, the one that has the fewest members, fewest joints, whichever method that you think makes sense. There's no wrong answer, but I need to know why you picked one, okay? I need you to lay that out. Because what I'm going to have you do on submission 2 is I'm going to have you reflect on that and basically, do you think you made the right choice? Would you have gone back and changed it? Et cetera. So that's sort of the point of where we're at now. Okay, any questions? Okay, so again, my goal, as I mentioned in the lecture where I discussed the project, my goal is I don't really want it to be a terrible amount of work. It shouldn't be, and the way I've engineered the week before Thanksgiving break, we'll have a lecture on Monday. Wednesday will be us working on submission 2. You can come if you want. The attendance will be voluntary that day. And then Friday we'll have canceled class. So the Friday before Thanksgiving break, no class. And then that's that, right? Unless you want to have class the Friday before Thanksgiving break. Now I get more of a reaction. I see how it is. All right. You got what you wanted, and now you're just like, okay, move on. I see how it is. Okay. All right. Let's get into the topic today. So we're going to discuss shear and moment diagrams for frames, and I'm almost hesitant to even bring this up again because I've been bringing this slide up a lot. But I think the big point that I keep trying to get across is that nothing really changes in our relationship from when we're constructing shear and moment diagrams from the past few lectures. I mean, we're using the same relationship, but we've done it for concentrated loads, distributed loads, concentrated moments, fixed supports, pin supports. Like, it's still the same idea. It's still the same concept. Nothing's really any different, okay? So we're still using the same differential equation, or differential relationship, I guess I should say. We're still using the same graphical conclusions, between load and shear and moment. That hasn't changed, okay? And it's not going to change when we construct shear and moment diagrams for frames, which is our topic for today. And so to point blank asks the question, does the process for constructing a shear and moment diagram change when we're looking at a frame? Not really. It really doesn't. Really, the only difference is that we're plotting the shear and moment diagrams. We typically plot them parallel to the members. So in order to do that, we're actually going to be plotting. So for example, when we look at the columns, we're actually going to be plotting the shear and moment diagrams this way, or this way for beams, etc. So if we had, let's say, a member that was at an incline, we might plot them this way. So we really, we're just treating it like a beam that's just rotated. One thing that we are going to have to do is we're going to have to cut sections, though, with frames, because when we draw the shear and moment diagrams for a frame, so for example, let's look at this frame and let's look at the column, okay? So the idea with this frame, just to make sure everybody's on the same page, so this frame has essentially, it's sort of a portal frame like this. So we've got a distributed load right here, distributed load right here, distributed load right here. We have a reaction of 42 kips, reaction of 18 kips, etc. We also have an 18 kip load right here. Okay. The idea is that when we plot the shear and moment diagram, we have a reaction here of 18 kips. Okay. When we plot the shear and moment diagram, let's say of this column, well, we can start here, but working our way up, we actually need to know what the internal response is right here at this joint in order to be able to finish, in order to be able to terminate the shear and moment diagrams. So we're going to cut a section at the joint and look at the internal response there, and we'll do that for every member, okay? For the frames that we're going to look at in here, we don't really need to go off to the side and look at the joints themselves, but sometimes you do. So for example, if we had a frame that, like let's look at a really, really big frame. Let's look at a frame that, I don't know, looks like this. And let's just assume for the sake of discussion that we can analyze it. We have all the reactions. We're not worried about determinacy or anything. So what we'll do is we'll look at the equilibrium of this beam, this column, and this column. And what we might do is a separate investigation just of that joint, just to make sure that if we look at all the forces and moments at that joint, that it's in equilibrium. We aren't going to have to do that for our frames, and this is something that, for example, if you're using software to model a more complex frame, the software sort of handles that for you as long as you've modeled it properly. That's usually not the biggest concern. That's not to say that you shouldn't understand how to investigate it, and there are some unique examples where you might have to, but if you can do what we've been doing so far, this isn't really too much of a big ask. It's just equilibrium like we've been doing this whole time. So to illustrate, I kind of want to just go through an example. So we're just looking at a two-member frame. My philosophy is that if you can construct shear and moment diagrams for two-member frames, you can construct them for n-member frames. It doesn't really matter. It's all kind of the same thing. So I have a frame that has member AB and member BC. So just to be clear, if I use the term beam in this example, I'm going to be talking about this horizontal member, this member BC. And if I use the term column, I'm going to be talking about this vertical member AB. So I might just, as I'm going through the verbiage, if I just use the term column and beam, that's what I'm referring to. The column is the vertical member, the beam is the horizontal one. I went ahead and gave you the support reactions on this problem. I don't believe that at this point that should be anything to write home about. I mean, we have 60 kips going to the right, so that means we have a 60 kip load reaction at A going to the left. We have 75 kips down, and we ultimately have 75 kips up. The reason for the difference is that, we've got this load a little bit off here. We've got that, so that reaction needs to be a little bit different than AY in order to meet equilibrium. But we can easily investigate and see that it meets equilibrium. We've got 60 times 10, 75 times 10, and then 45 times 30 if we sum moments a day, and that'll be pretty easy to show that those equal one another. Sound good? Okay. All right. Let's see. Okay, I'm going to scroll down a little bit. I'm going to give everybody a sec to sort of jot this frame down, then we'll get to it. We'll start off with the column. So we'll start off with a free body diagram. Free body diagram of column AB. So what I'm essentially doing with this free body diagram is you can sort of think of it as I'm cutting a section like right here. So I'm going to cut a section right here, and I'm going to cut a section right here. So basically right before the joint, there's no real distance there, so it's sort of like infinitesimally away from the joint. But basically what we're doing is we're cutting a section and we're looking downward. Okay, so we're going to draw the free body diagram. Now I want to be clear on something when I cut this section. Am I cutting through a hinge? No, there's no hinge at point B. So if I'm not cutting through a hinge, how many unknowns am I going to have at this section cut? 3, right? I'm going to have a vertical, a horizontal, and a moment, right? Because from an analysis perspective, I'm cutting through an arbitrary point in the structure. Now, it's not arbitrary from a strategy perspective. I made a conscious decision to cut the section at B, but it's not a hinge. It's not a location that has a release. Okay. So when I draw this free body diagram, let me sort of get this set up. Okay. So I've got, here's my member. Okay, I've got a 60 kip load right here in the middle. And then for reactions, I have, so we'll draw this, we'll say AY is 60 kips, AX, sorry. This is AX is 60 kips, and AY is 30 kips. Okay, let me put some dimensions on here to make sure we're all on the same page. So this is 10 feet. This is 10 feet. So when I cut the section, again, I'm going to have 3 unknown forces here at point B. Okay, but I think for the most part we can identify those forces just visually. Okay, so let's just apply our equations of equilibrium in sequence and let's see what's going on. Let's start off with the sum of the forces in the x direction. Okay, so can somebody tell me, so there's going to be an unknown horizontal force, an unknown vertical force, and an unknown moment here at B. What is the unknown horizontal force going to be? 0. And how did you get that? Yeah, you have 60 going to the right, 60 going to the left, they cancel. So we're going to say Bx is 0. Okay? All right, does that make sense? Okay, so we have also our sum of forces in the y direction. So can somebody eyeball this and tell me what's the vertical force going to be at B? 30 down. Why 30 down? Because we've got 30 going up, right? So what I'll do is I will draw this right here. So let me sort of indicate where I've cut the section, and let's draw a downward force like that, and let's call it By is 30 kips. And so we'll say By is 30 kips going down. And then if we want to be maybe a little bit more scientific about it, maybe we ought to sum the moments at B. Maybe we ought to be a little bit more formal about this one because we got a little bit more going on from a moment standpoint. So if I sum the moments at B, I've got 60 times 10 this way, 60 times 20 this way. Does the 30 kip reaction cause any moment? No. Does the By cause any moment? So all I've got is I've got 60 times 10 and 60 times 20. So I can do the math in my head and say this is 1200, this is 600. I need a little bit more moment over here. So MB is that, right? So 1200 foot kips is MB plus 600. Goodness, getting tangled up with my mouse here. So, okay. So what I've got is I've got this. MB is 600 foot kips like that. I don't need that simple because I already drew it. All right. Does that make sense? Everybody with me on that? So what I'm going to do is, just for the sake of discussion, just so I have it here, okay, so what I'll do is I'll sort of draw that, so that member right here, so this is where we cut the section, okay, and what we got was we've got this, and then we've got that. And I'm just copying what's on the screen here so I don't have to keep scrolling. But I wanted to sort of have just like a small little reference for what I got right here. Okay? Everybody with me so far? Okay. Any questions? Any questions? Okay. All right. So what I'm going to do now is I'm going to take a little bit of a break. And now I want to do kind of the same thing, and I want to investigate the free body diagram of the beam. So everything I just did, I kind of want to repeat it, but I want to repeat it independently. And you'll kind of see what's going on here. Okay, you'll kind of see what's going on. All right, so bear with me. So now what we're going to do is the free body diagram of beam BC. Okay? Let's do the free body diagram of beam BC. So I'm going to kind of handle it the same way. I'm going to draw the free body diagram, assuming I cut that section right at B. Okay? So I've got a reaction here. That's reaction CY, and that was 45 kips. And this is a vertical load of 75 kips. And that was placed 10 feet from B, so that makes this 20 feet, because the member is 30 foot long. Am I right? Yeah, 30 feet. Okay. All right, so we're going to go through the same process. All right, so let's sum forces in the x direction. Okay, so looking at the beam, what is the horizontal unknown right here at this joint? 0. There's nothing going on horizontally, so bx is 0. Okay. What about summing forces in the y direction? Okay, so let's chew on this a little bit. I have 75 going down, I have 45 going up, so what's got to happen here? 30 going up. Okay, so by is 30 kips going up. Okay, now same thing, I'm going to sum moments at B. I'm going to try and be formal about that. All right. So here, let me do this. Let me put my little vertical force here. All right. Okay. So we're summing moments at B. Okay. So what do I got? I've got 75 times 10. 45 times 30. Okay, so see, 45 kips times 30. I believe that's 13,500 or 1350. Let's see, 1350. And then 75 times 10. I can do that one in my head. That's 750. So I'm going to need a little bit more moment on the left side. So we're going to call this MB. Put that over there. So MB plus 750 is 1350 foot kips. So therefore, MB is plus 600, and then it's going this way, right? So MB is like that, okay? Does that make sense? So just to be clear, okay, so if I look at that free body diagram over here, right, so the rest of the beam is all the way over there, and this is where I cut the section. What I got a vertical force and I got a clockwise moment of that, okay? Y'all kind of see what's going on here? So what would happen if, just to, let's consider what's going on here on this whiteboard is the joint equilibrium. What would happen if I superimpose these forces on top of one another? I've got 30 up, 30 down. What do they sum to? I've got 600 clockwise, 600 counterclockwise. What do they sum to? 0, right? This is what I meant when I said ensuring that you have joint equilibrium, right? So, for example, if you had a member that had like 4 members framing into it, what you might do is you might look at all of the forces from all of those and sum them all up and see if you get zeros across the board. And if you did, that just means that you've met your joint equilibrium. Does that make sense? So you would just do it with multiple members. So that's all that means. It's just ensuring, so if you do everything independently, you should be able to superimpose all those forces and get net zero, or forces and moments, I should say, and get net zero across the board. Make sense? Okay, I figured that would be pretty easy to follow. I just wanted to make that point. Okay. So now the only thing left to do is to construct our shear and moment diagrams. And again, I don't think you're going to find this is fairly difficult. So we'll do the odd one first. We'll do the column. That's the new one. So what I'll do is I'm going to try and do this the same way I've done shear and moment diagrams in the past. I'm just going to try and do it this way. So what I've got, I'm going to redraw this free body diagram. Okay. So I've got, let's see, 30 kips. I've got 60 kip left. Kips, right? Let's see. I've got 600 foot kips like that, and then 30 kips down. Okay. So let me put my dimensions on here. So this is 10 feet apiece. Now, one thing I am going to place here on this free body diagram, which might seem a little innocuous, but there's kind of a point to it, is I'm going to place my labels. And what I mean by that, I'm going to say this is joint A, this is joint B, okay? there's a reason I'm making such a big hullabaloo about the labels. Okay. Later on, we're going to learn how to model these structures using software. And the software isn't going to know any better in terms of member labels and things like that, because ultimately what it's going to do is what you tell it to as an analyst. Okay. Typically, the way that a software package will construct the shear and moment diagrams for a structure is it will construct them based on the order of nodes, what I'll call nodes, N-O-D-E-S. So nodes and joints, I use those terms interchangeably. We'll talk more about that later. But so in a software program, the joints are not going to be lettered, they're going to be numbered, right? Because I mean, you could have a structure that has more than 26 joints, right? So what the software program will do is it will construct the shear and moment diagrams from the order of lower number joint to higher number joint, or in this case, lower lettered joint to higher lettered joint. So when I construct the shear and moment diagrams, what I'll do is I'll construct them over here. Normally the software package will just plot everything on top of one another, but let me see if I can do a little better on that. Let me see if I can move that up just a little bit. Okay. But what the software package is going to do is, let's say here's my shear diagram. It's going to start at the bottom and it's going to work its way upwards. Okay. And the reason it's doing that is because I'm assuming that as the analyst, when I was defining the joints, so when you define joints in a software program, it's basically X, Y, and Z of joint 1, X, Y, and Z of joint 2, X, Y, and Z of joint 3. You're entering in coordinates. And so the idea is that I would enter this coordinate first, then this one. And so when I define the member, I draw it from this joint to this one. And so that's going to define the direction in which it plots the shear and moment diagram. That's never really been a big problem for a beam, because from a software perspective, you would assume that you would just define it from left to right, which is the way we've been constructing them. But the reason I go into that is because if we were to, let's draw the shear and moment diagram this way, and then let's think about what would happen if we drew it the other way. So this is going to be our shear diagram. Okay, and again, we're going to start at 0, and we're going to assume that we start at 0, hopefully we end at 0, okay? So how does that work? Well, we're looking at the beam this way, and so we're thinking about shears. Shears in this case, I want you to think transverse loads. So the member goes this way. I want you to think of shears, the loads that cause shears going this way. So if I see this 0, what does the column tell me to do? What's the first thing I need to do? If I'm at 0, what do I need to do? I need to follow this load and go to the left 60. Does that make sense? I'm going to go to the left 60. What happens from A to here? Nothing, right? And on a shear diagram, nothing means constant shear, right? So what I'm going to do is I'm going to go over. I'm going to go up, and then that's going to tell me to come back down to 0. And so that's going to be 60. That's going to be 60. If you want to think of that as negative 60 because you're going to the left as opposed to the right, that's fine. It doesn't really matter all that much as long as you get the general understanding. Does that make sense? So that's your shear diagram, right? So we're only thinking about the transverse forces. So we go over 60, down, back 60, nothing here. That's our shear diagram. How do we go from a shear diagram to a moment diagram? Bless you. We take the area under the shear diagram. What is the area of this rectangle right here? 600, because it's 60 wide and 10 tall. So we'll call this 600. I'm going to call it positive, and if you're wondering why I'm calling it positive, I'm essentially saying that that's my x-axis, and we'll say that's my y-axis. That's why I'm saying that's positive. So if you want, we'll go ahead and call that positive too. So we'll draw our moment diagram here. Okay. So we'll start at 0. So if everybody's paying attention, I want you to tell me what to do. What do I do here? What I take the 0. What do I do? linear increase to 600. So I'm going to go like that, right? So that's going to be 600. And just so we're making everything make sense, what's the slope of that line? 60. Okay. 60. Okay. What happens from the middle to the top? What, straight up, right? And then what happens right here? And why do I go down to 0 right here? Exactly right. So that's your moment diagram. That's it. Again, really all we're doing is we're just drawing the shear and moment diagram just flipped up. That's all we're doing. So far, so good? Now, let me ask you a question. And let's just look at the shear diagram just to make sure we're all on the same page. I drew the shear diagram from the bottom working my way up. Can anybody see what would happen if I drew my shear diagram on the top working my way down? What would happen to the shear diagram? It would flip over, right? Because what would happen, I would go down, and this would tell me to go this way, over, and this way, right? Does that make sense? That doesn't mean that it's wrong. It's just if you were, as the analyst, expecting it to look like this, and it looks like that, a simple answer would be you flip your nose, you flip your joints, you drew your joints in the opposite direction. Doesn't mean that the analysis is wrong. It's just plotting it opposite the way you expect it. Okay? Sound good? So I just mentioned that just to make sure that, you know, when you get into software land that you kind of know what it's doing. Okay. And again, that's the weird one. The simple one, shear and moment diagrams for the beam, that one's going to be easy. Because this is going to be exactly what we would expect. For a typical beam. We have this. This is 45 kips. We have that, which is 75 kips. We have this, which is 30. We have that, which is 600.
That 600 goes here.
You're right. Yeah, you are right. It does. Thank you. Okay, so this one just same as before. Again, I'll label my joints just to make sure that when we plot our diagrams, we're going in the proper order. So we'll start at 0, and I think we can walk through this one pretty easily. We'll jump up to 30, go over. At 30, we will drop down 75. If I drop from at 30, drop down 75, what am I at? Negative 45. 75, yeah. 30 down 75, negative 45. Then go over, hop back up to 0. Okay. Same story as before. I'll now integrate the shear diagram. So 30 times 10, that's positive 300. 45 times 20, negative 900. We don't add up to 0, right? But what do we add up to? We add up to negative 600, right? So how are we going to correct that? At the very beginning of the beam, we're going to have a 600 jump in which direction? up, right? So when I construct my moment diagram, I'm going to jump up 600, linear increase to 900, and then a sudden decrease to 0. And then again, we can look at the shear diagram and see, okay, this has a slope of positive 30, and this has a slope of negative 45, and the figure bears that out, right? Because you can kind of see this line is steeper and it's negative. This is, you know, a much gentler slope and it's positive. Make sense? Any questions? So what I will say is I think at this point, I'm done with shear and moment diagrams. I think we've done it. We've run it into the ground, but I do it because, I mean, every day that we've covered shear and moment diagrams, we've covered a different aspect of them. And by now, hopefully you realize two things. One, this is pretty easy. And two, you should be able to construct a shear and moment diagram for just about anything, right? I mean, all it is just different pieces, adding it together. It's just basic equilibrium, basic geometry. And for the most part, we haven't had to do much in the way of calculus, which is always kind of nice. Any questions? All right. I do want to mention a couple other things, and then I'll give you some time of your life back. What we're going to be doing next is looking at deformations, looking at deflections. So with trusses, remember with trusses, we looked at all different ways we could analyze a truss, a method of joints, a method of sections, and then we looked at deformations. We looked at how much would a truss deform under applied load. And if you remember, we had a method of doing that, and that method was the method of virtual work, or the unit load method, right? So we would analyze the structure twice. We would analyze the structure with the loads as is, and then we would do a virtual analysis. Remember how the virtual analysis would go? We would kick off all the loads, and then we would replace all the loads with just a single unit force where we wanted to find the deflection in the assumed direction, right? And then we would analyze the structure again, sum up our energy, and that was our answer, right? We're going to do the same thing with beams. Same process, same method. There is one key difference, though, in the nature of the problem, okay? And so let me sort of explain that in a nutshell, okay? So if we're looking at a truss member, let's just keep this kind of basic. Let's say I have a truss member and I put 20 kips on either end of it, okay? So if I put 20 kips on either end of it, here's the structure, here's the system. If I cut a section right here, the internal force inside the truss member is 20 kips, right? If I cut a section right here, the internal force is 20 kips. If I cut a section right here, right here, right here, it doesn't matter where I cut a section, the internal force inside this truss element is 20 kips. Does that make sense? Okay, so what this led to was us being able to do this. It led us being able to do that, just sum up some terms, right? Okay. The problem, though, with a beam is it doesn't really work like that for beams, okay? For beams, okay, so if I put, I don't know, 10 kips, let's just make it simple, 20 kips. Do I get the same moment if I cut a section here than if I do here? The moment changes, right? And it doesn't matter, like, with a truss member, it doesn't matter where I cut the section, I'm going to get the same internal response. For a beam, though, it does. Because by the nature of a shear and moment diagram, the internal response changes depending upon where you look, right? So what this is going to mean is this, okay? So I'm going to be able to sum up some terms. And so for moments, instead of little f and big F, I'm going to have little m and big M. Instead of EA, I'm going to have EI. But instead of being able to just multiply by the length, I actually am going to have to integrate. We actually are going to have to do some calculus because we're going to be summing up the energy across the span, and unfortunately, the energy is a function of the moments, and the moments change. Okay, so we actually are going to have to break out some integrals. That's the bad news. The good news is that the integrals that we have to do are really, really easy. Let me ask you a question. What's that? Then you're good. I'm kidding you. I kid you not. That's like the hardest one we do. It's really basic stuff, okay? Most of the integration that we're going to have to do is stuff like this. Or more specifically, maybe like that. That's actually an integral from like our first example in class. Like that one right there. So if you can do that, you're pretty good. And the nice thing is this will do it for you, right? So I throw that out there just to say that, yes, we are going to have to do it. Yes, there's a real application. So if you're wondering, are we ever going to use calculus? Yes, we're going to use it. But trust me, it's going to be really easy, okay? And so I just throw this out there just to make sure that you, when you start seeing the little integrals that you weren't totally surprised by. Okay, I'm giving you 9 minutes of your life back. I'm going to pull up the code, but that's all I've got. I will see you all on Friday. And don't forget your projects submittal one's due on Friday. That's all I've got.